Okay, so heat capacity, guys, as I mentioned yesterday, is just a physical property of all matter, in the same way that solubility is a physical property of all matter. Okay, so every single substance is going to have a different heat capacity, okay, or specific heat capacity in this case. So what we're going to be looking at is a little bit of what it is, and then a little bit of how to solve problems related to it, and then we're going to move on to latent heat, which is similar, okay, simple problem solving, and then we're going to move on from there. Okay, so heat capacity, okay, and specific heat capacity specifically, okay, is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay. So the specific heat capacity of a substance, like we said, is a characteristic physical property, and it is always the same for any amount of that substance. All right. Now we were saying the other day, okay, that water has a high heat capacity. Right? That means it can absorb a lot of energy before it increases in temperature. Okay? And similarly, it can release a lot of energy without a big change in temperature. Okay? That's why being close to the ocean has such a big effect on your climate, because you've got this vast heat energy reservoir beside you, okay, that is constantly going to be pumping heat into the air or absorbing it from the air, okay, and regulating the air temperature, because it can do that without changing its temperature very much. Okay? So basically, in your workbook for this unit, okay, so if you go into Google Classroom and you go to classwork, okay, and you go down to course materials here, and you go to worksheet packages, in here for unit 4, okay, will be your chart of specific heat capacities. Okay, so that's basically the first thing in there. All right. Now the units for specific heat capacity are joules per gram degree Celsius. Okay, because it's the amount of energy in joules required to heat 1 gram by 1 degree Celsius. So that's why the units are the way they are. Okay, so for aluminum, okay, aluminum only requires 0.9 joules worth of energy to heat 1 gram of it by 1 degree. That's a low heat capacity. Okay, it's on the lower end. It's not super low, but it's on the lower end. Okay, brick, on the other hand, has a heat capacity of 3 joules per gram degree Celsius, which means it takes a lot of energy for brick to change its temperature. Right? It's why even though the sun can shine on the side of the gym over here, okay, all day long, you can go over there and lean on it, put your hand on it, and it won't burn. Okay? If it was made of something else, okay, with a lower heat capacity, it would change its temperature a lot. And when you put your hand on it, it would be very, very hot. Okay? If you did that with, let's say, a black car, okay, so you put your hand on the hood after it's been in the sun all day, it's going to be pretty hot, okay, because steel, or if it's made of aluminum, it's got a much lower heat capacity, and as a result, it would have heated up quite a bit more. Okay, does that idea make sense to everybody? Okay, so you can see here there's quite a range, okay, of heat capacities. Concrete's 2.9, copper is pretty low. Okay, copper will heat up very quickly. Glass, kind of in, it's kind of on the lower end. Gold, okay, gold is a really low heat capacity. It's why you can put on jewelry and like feels cold for an instant, and then all of a sudden it's the same temperature as your body. Okay, it doesn't take very much energy for it to heat up. Okay, human body on average 3.470 joules per gram degree Celsius. That's because we're mostly water. Okay, and water has a very high heat capacity, so we're on the higher end of that. Okay, ice, 2.116. Here's the weird thing. Is ice water? Yep. It is. But because water is a polar molecule and basically disobeys every rule that we all know apply to everything else, ice, water, and steam all have different heat capacities. Strange, but true. Okay, that's not true for everything else. Okay, so you can see there's quite a list here of things. The highest heat capacity is hydrogen gas. Okay, 14.4 joules per gram degree Celsius. So it takes quite a bit of energy to heat up hydrogen. Okay, and helium, similar. It's also fairly high. That's why they're used to keep things like superconductors cold. Okay, in places like power plants and stuff like that. Okay, all right. okay with that idea? So the formula that's going to apply to specific heat capacity is this one. E equals m times c times delta T. Okay? E stands for energy in joules. M stands for mass in grams. We're back to chemistry now. Okay? In physics, everything had to be in kilograms. Where this is back to chemistry, so now mass is back to being in grams. Okay? And then C is the specific heat capacity, so you would need to know what substance you were dealing with, so you could look that number up and plug it into the formula. And then delta T is the change in temperature, so final temperature minus initial temperature, or sometimes the question just says it changes temperature by 55 degrees, and you plug 55 in for that. Okay? Everybody all right with how that works? Okay? Is it going to be a pretty easy formula to use? Right? I mean, if I want to solve for energy, all I have to do is multiply three numbers together. Okay? That's pretty easy. If I want to solve for anything other than energy, I just divide the other two things over to the other side. So if a question wanted me to solve for mass, I would just divide both sides by C delta T, and I'm done. Okay? So it's because they're all in a line, it's really, really easy to manipulate and use. All right. Questions on that? Okay. There's really not a whole bunch else to tell you about heat capacity. Okay? It's not going to challenge your mathematical skills. Okay? And the concept itself is higher heat capacity means heats up slowly. Okay? Lower heat capacity heats up quickly. That's really all that you need to know. Okay? The big application of that is why oceans can affect climate. Okay? That's how they're related. That's how it's related to basically the other stuff we've talked about in this unit. All right, copy this one down. We're going to walk through an example of each way I might ask a specific heat capacity question because, spoiler alert, you're going to get a heat capacity question on your unit and final exam. Okay, so for this particular question here, again, same as any other problem-solving thing we've done in this course, the first step is write down your givens. Okay, so it's asking how much heat. So that means we're solving for E. Okay, is needed to raise the temperature of 150 grams, so that's our mass, okay, of water, which has a specific heat capacity of 4.2 joules per gram degree Celsius. Okay, from 5 degrees to 85 degrees. So what's my temperature change? 80. All right, so I've got M, I've got C, I've got delta T. Okay, so E equals MC delta T. I plug in my numbers, 150 times 4.2, oops, 4.2 times 80. So we've got 150 times 4.2 times 80. All right, 50,400 joules worth of energy. Okay, that's why we have such big power draws on things like stoves. Okay, to heat up water requires a lot of energy. Water has a very high heat capacity. 50,400 joules. That's about as easy as they get because you didn't have to manipulate the formula. Not that manipulating this formula is going to challenge your math skills. Okay. Any questions on that one?
How many marks would that be?
This would probably be like a 3-mark question because there's so little to do. 1 mark for givens, 1 mark for the formula and plugging in numbers, and 1 mark for the answer. Okay. Copy that one down and give it a try. Then we'll walk through it. Okay, so for question number 2 here, okay, it's asking what material this cup is made out of. So my givens are that I know the mass, okay, it's 100 grams. and I know that it's going to take 4,200 joules, so that's E, okay, to raise its temperature from 12 to 62 degrees, so that means the temperature change is 50 degrees Celsius. Okay, what part of the formula do I not have? C. Would solving for C help me figure out its identity? Yeah, because specific heat capacity is a physical property that is unique to each substance. All right, so C is the thing I'm looking for here. So we'll have E equals mc delta T, and we're going to solve for C by dividing both sides by m times delta T. Okay, and so what we will be left with is that C equals E over m times the change in temperature. You will need to make sure that on your calculator you do the bottom as an entire operation. Don't write it in left to right, or it'll do it from left to right and gives you a different answer. Okay, so we've got 4,200 joules on the top divided by 100 grams times 50. Okay, so if I go to 4,200 and divided by 100 times 50. All right, I get 0.84 for my specific heat capacity. 0.84 joules per gram degree Celsius. So now what I do is I go to my chart and I look, oh, there it is right there. 0.84 joules per gram degree Celsius is the specific heat capacity of glass, okay? Which would make sense. Okay, given the context of the question, that it wouldn't be made out of hydrogen gas. Okay?
So we're gonna not just put on the final.
You will have any specific heat capacities you need for the test. I'm not gonna put this chart on the test because this is way more than you would need. Okay, so on a specific question, I might say it's made out of gold, and it's and I would write 0.130 or something like that.
Yes. Okay, thank you.
Okay. All right, everybody okay with that one? Okay. Right. This is about as tricky as they get. Okay, you're looking for the final temperature in this one. Okay, of a 185 gram block of iron, initially at 7 degrees, if it is heated with 200 joules worth of energy. I'm going to give you a couple minutes on that one. Okay, so let's have a look at this one. So on this one, we're looking for the final temperature. So we're looking for TF. We are given the initial temperature. Okay, 7 degrees Celsius. Okay, the other things we're given, we're told that it's iron. So we know that C is 0.460 joules per gram degrees Celsius. Okay, and we know that 200 joules worth of energy are used to heat it, and that there is 185 grams of it. All right, so we have E, we have M, and we have C, and we're looking for final temperature. So we've got to solve for temperature change first. Does everyone follow my reasoning on that? Okay, so E equals M times C times delta T, okay? And I'm going to solve for delta T by dividing both sides by M times C. So that then will be 200 joules divided by 0.460 times 185. Okay, so this block of iron is going to change temperature by 2.35 degrees Celsius. So if its initial temperature was 7, what's its final? Well, what's 7 plus 9, or plus 2.35? 9.35. Okay, so my temperature change is 2.35 degrees Celsius. Okay, temperature change is final temperature minus initial temperature, right? Delta always means final minus initial. Okay, I know the initial, so I'm going to add it over here. So delta T plus Ti will give me TF 7 plus 2.35 equals 9.35 degrees Celsius. That's as hard as they get. Okay, just because it has an extra step that involves calculating one of the two temperatures involved. questions on that. That one would probably be out of 5. One there. 1, 3, 4, 5. Okay. Anyone need that one anymore? All right, so on that worksheet that's in your notes package, you have these questions. Okay, looks like this here. Okay, we got heat capacity worksheet, and we've got on there 32 questions. You're not going to do all 32, okay? Because the way it's set up, at least initially, is that like the first 4 questions are all asking you to calculate C. So they're all exactly the same calculation, okay? And then it asks you from 6 to 10, it asks you to calculate the energy and so on. So I'm just going to pick a few questions here at random. You can, and then you know which ones to do. So maybe just write down these numbers, okay? So you know which ones I want you to do. So I am going to have you guys do number 2. Number 4, 6, and 7. Nope, 6 and 8, 11, and 15. 17 and 19, and let's say, so that'll be 1, yeah. Okay, so that gets us calculating some masses, some temperatures, yeah, okay. So those are the ones I want you to do. 2, 4, 6, 8, 11, 15, 17, 19. Okay, I'll give you a little bit of time on those. If we need to, we can walk through them together, and then we're going to talk about the latent heat stuff after that. Okay? Okay, any of those giving us trouble so far, guys? We gotta look at the latent heat part of this now, okay? I'm gonna teach you about the heating curve of water a little bit, but you're not gonna have to do any problem solving to do with the heating curve of water, just with the two parts where state changes, okay? All right, so latent heat is this thing we talked about back when we were talking about climate and energy transfers. It's that heat that is part of the water cycle. Okay? When water evaporates from somewhere, let's say near the equator, okay, it becomes a vapor, it requires a lot of energy to do that. The water vapor then holds that energy, and as it moves due to wind, it carries all of that energy, which we call latent heat, to another area. When that water vapor condenses in the new area, the energy it had in it is released. Okay, so it's another way to move vast amounts of thermal energy from one place to another. Okay? What we have to understand is there's two types of thermal energy, just like there's two parts to mechanical energy. Okay? There's kinetic and potential, and it's the same for thermal energy. There's kinetic thermal energy, and there's potential thermal energy. Okay? So you have to think back to when you first learned about the particle theory, grade 8 probably. Okay? So in the particle theory, it says that everything is obviously made up of small particles. Okay? And in solids, those particles are arranged how? Are they far apart or close together? Really close together. Okay? So in solids, the material, when a material is in its solid form, so let's say ice, okay, the particles don't move very far. Okay? They're kind of locked in place, and they don't have very much potential, in fact they don't have any potential thermal energy, because they can't get any closer together. Everyone follow me there? If I heat up a solid, what do the particles start to do? They start to move. Right. They can't move past each other, that's why a solid can't take the shape of its container, but they can start to move faster, and when they move faster, they run into each other, and that's how conduction works that we talked about yesterday. Okay? When I get that material heated up enough that it gets to its melting point, the particles can't move any faster in their current arrangement. So, they move apart. When they move apart, the substance goes from being a solid to being a liquid. Okay? During that time, the temperature of the substance doesn't change. Okay? Temperature measures the kinetic thermal energy of the substance, of the particles, basically how fast they're moving. Okay? Potential thermal energy is related to what state is the material in. Once the material melts and the particles can move apart from each other, okay, they now have the potential to go back together. And when they do that, they'll release all the energy that was required to make them move away from each other. Everyone kind of follow me there? Okay? So that's what we're seeing in this diagram here. Okay? This is for water. This is the heating curve of water. So if I have a block of ice at minus 25 and I add heat to it, okay, its temperature increases. It doesn't melt, not right away. Okay? Ice doesn't melt until it gets to what temperature? 0. Okay, so I add heat, okay, and what happens is the temperature of the object, of the material, in this case ice, changes. Okay? So it gets up to 0 degrees Celsius, and then the temperature stops changing. And what does the ice do? It melts. Okay? So for thermal energy, you can only change the kinetic energy or the thermal energy. Or the potential energy. You can't change both at the same time. In mechanical energy, you can change both at the same time. Okay? You do work, you can change both. But for thermal energy, you can't. So when I heat something up and I change its temperature, I change the speed at which the particles move. When I change its state, I change how far apart they are. Right? Changing state takes way more energy in general than changing temperature. It takes way more energy to change the potential thermal energy of a material than it does the kinetic thermal energy of a material. Right? So if we look at this, the bottom of this graph, the x-axis, is the amount of energy that's being added. So to change the temperature of ice from minus 25 to 0 requires only this much energy. Okay? It's very, very little. In order to melt that amount of ice, I need this much energy. Is that considerably more? It is. Okay? It takes a lot of energy to change the state of something, ice in particular. Okay? Once all the ice has melted, now I continue to add heat and the temperature of the water starts to rise. Okay? But it won't start to rise until all the ice is gone. Okay? You can actually try this at home. Right? If you have a thermometer, okay, and you put it in some water and then kind of well, I wouldn't say freeze the thermometer in the water, but freeze a bit of water, or just take some ice cubes out of the fridge, okay, freezer. They won't be ice cubes if they're in the fridge. Take them out of the freezer, okay, and you can just put them on the stove and just start stirring them, okay. You'll see that the temperature goes up to 0, okay, and then stays there until all the ice is gone, provided you keep stirring it, okay? And then if you add heat to that, it'll get all the way up to 100, and once it starts to boil, temperature will flatten, okay? It'll stop increasing until you boil off all the water, and then it'll measure the temperature of the pan, okay? Because you can't capture the steam, okay? You don't want to do that. Okay, so I'm going to add some more energy, okay? I'm going to add now enough energy to heat the water from 0 to 100, which only takes this much energy. So a little more than it took to melt it, but it's a big temperature change. Okay? Once I get to 100, then the temperature stops changing, and look how much energy I have to add. This is the bulk of the graph, vaporizing the water. Okay? That takes the bulk of the energy here. Okay? Moving particles from a liquid state where they're separated, and a liquid can take the shape of its container because they can move past each other, to a gas, okay, even further apart, takes way more energy than anything else, okay, that vaporization. So all of this energy that I put in to vaporize it is now stored in the vapor. That's the latent heat we were talking about that can be an energy transfer on a global scale. If this water is evaporated at the equator and then moves towards the pole, when it condenses, all of this energy will get released. Okay? Which would burn you worse? Water at 100 degrees Celsius or steam at 100 degrees Celsius?
Steam.
Why? They're both 100 degrees Celsius.
There's more energy in steam.
Exactly. Okay? This is where water is. This is how much energy water has at 100 degrees Celsius. This is how much energy steam has at 100 degrees Celsius. Okay? When the steam hits you, immediately it condenses onto your skin, and it releases all of the energy that it had stored as a gas, because now it's going to be a liquid. Okay? That's why steam burns you way worse than water. Okay? I mean, usually steam is also hotter than water, but it's not so much about how hot it is as it is how much energy was stored in it, because it's a gas and not a liquid. Okay? So steam is far more dangerous in terms of its ability to burn you than liquid water would be. Okay? Even if they're both at 100 degrees Celsius. Making sense? Okay. So that's really all you need to know about how the heating curve works and how it's related to energy transfers. Okay? That's why we said that within the water cycle, a lot of energy is being stored and transferred and moved around. Okay? This is why, because of the heating curve. Go ahead.
When you're boiling something on the stove,
Yeah.
and you put your hand over the pot,
Yeah.
why doesn't it burn? If it's already so hot.
Well, it's dispersed, right? Like if you had a whole bunch of steam coming out of the pot and you put your hand in, you'd burn. Okay? Or if you had like a tea kettle and it's shooting out the little jet of steam, don't put your hand in that, right? Because it's concentrated. But over the area of a pot, and as long as you're not too close to it, you're probably not going to burn yourself. I'm not saying try this at home. Okay, but certainly it has a chance to then disperse. But you can feel like as you start to get closer to that steam, the air around it is considerably warmer, right? And that's not just because the stove is on. Does that make sense?
Yeah.
Yeah. Okay, so the things that are important for us here are these two formulas. Okay? The formulas that calculate how much energy is required in a state change. Okay? There is specific latent heat of fusion. That has to do with melting and freezing of water. Okay? And specific latent heat of vaporization. That has to do with evaporation and condensation of water. Okay? So, the latent heat of fusion, LF, for water, is 333 joules per gram, and that's it. Okay? There's no degrees Celsius here because what doesn't happen while the ice is melting? There's no temperature change. Okay, because we all live in Canada, we've all had the experience of making a snowball with our bare hands. Okay? Do your hands get cold pretty quick?
Yep.
Okay. How cold is the snow? Well, if it's in your hand and it's starting to melt, it's at what temperature? 0. Right? Like, ice doesn't start to melt until it gets to 0 degrees Celsius. So you've got this ice in your hand and it's melting. Okay? Your hands get cold because obviously the second law of thermodynamics is taking place here. Energy is flowing from hot, your hands, to cold, the snow. But the snow is not really changing temperature. You're not warming up the snow, you're melting it. Okay? Now, here's why your hands get so cold. For every gram of the ice that melts, that will require 333 joules worth of thermal energy from you. Okay? That's why your hands get cold so fast. It's not that the snow is all that cold. When you put your hands in air at 0 degrees Celsius, they don't get cold right away. Okay? I mean, they'll get cold eventually, but they don't get cold right away. But you grab onto this snow and you got it in your hand, and suddenly your hands are cold really, really fast. Okay? It's because you're melting the snow, and the energy to melt that snow comes from you. 333 joules for every gram of ice that you melt. And you'll melt several grams probably while you're making the snowball. Okay? So you lose a lot of heat energy that way. Okay? Does that sort of make sense? All right, and the other number we need to know is the latent heat of vaporization. These numbers are on your formula sheet, so you don't have to memorize them. Okay, they'll be on the front page of the unit exam, and they're, like I say, on your formula sheet. Okay, so the latent heat of vaporization for water is 2,260 joules per gram. So that means that if you have water at 100 degrees Celsius, it will take 2,260 joules to vaporize 1 gram of water. And is that a lot of energy? It's a huge amount of energy. Okay, now, if you go for a run or you go into the weight room, you start working out, eventually what does your body start to do?
Sweat.
Why?
It's like all the water like ingested it coming out.
Yeah, it's coming out, but why does our body sweat? Like, what purpose does sweat serve? What does it do for us?
Oh yeah, like cools us down.
Okay, how does it cool us down? Because if you start to sweat, I mean, you start to feel cooler.
Like the sweat evaporates and just makes you colder, I guess.
Exactly. The sweat evaporates. And for every gram of it that evaporates, will require 2,260 joules worth of thermal energy from you or the surrounding environment. Is that going to make you feel cool pretty quickly? It will. Okay? That's why sweat works. Okay? Sweat is very good at cooling the human body because as it takes a lot of energy to evaporate water, and the bulk of that energy comes from your body. It's the same reason why when you get out of the shower, okay, before you get a chance to grab your towel and dry off, you feel a little bit chilled because all of a sudden, all this water that's on your body is starting to evaporate. Okay? And it's taking energy from your body to do it. Okay? One of the worst things that you can do if you're outside in the cold is get sweaty. Okay? That's why we always say you should dress in layers if it's cold outside. Okay? If you get working, you want to take off layers so you don't sweat. Because if you sweat and your layers get wet, once you stop working hard, that sweat's still going to evaporate and you're going to get chilled. Okay? So that's why we say dress in layers, so you don't get too sweaty. Or you only get one layer really sweaty, and you can take it off and put dry layers back on. Okay? It's the same reason why if you fall through the ice, okay, like if you walk on thin ice, which by the way, don't do, it's very dangerous, okay? But if you fell through that and then you were able to get back out, you could die of hypothermia. Okay? It's not that it's terribly cold, but you're soaking wet, and that water is going to evaporate. And it's going to take energy from your body to do it. Okay? Is that making sense? Okay, so that's kind of how sweat and stuff like that works. Okay, let's say I want to take some drinks out on a summer day, but I want them to stay cold. Where do I put them?
In the cooler.
Okay, do I put cold water in the cooler or do I put ice in the cooler?
Ice.
Why?
Because then it'll like go into cold water, I guess, after it melts. So,
Okay.
and it has like a lower melting point.
Partially. Let's go back to the heating curve. I put ice in there. Once I put the ice in there, it's going to be at 0 degrees Celsius. Okay? I could also put water at 0 degrees Celsius in the cooler, but which one's going to keep it cold longer? The ice. Why? Because this is where ice starts. This is where water starts. I get this additional ability to absorb heat energy from the ice, right? It's going to take 333 joules of heat to melt every gram of ice that I have in the cooler. If I just put water at 0 degrees in the cooler, it's just going to start warming up right away. Okay? The ice gets to change state first. That's why we put ice in drinks. Okay? You go to a restaurant or something like that, and you put the ice in your fountain drink. Okay? The reason we put the ice in there is because it will keep the drink cold. Okay? It will absorb heat energy from the surroundings, okay, in order to change state and keep it cold longer. Right? So there's kind of a logical, physical explanation for all these crazy things that we do. All right, so the calculations you'll be expected to do, okay, involve these two formulas. Energy equals mass times the latent heat of fusion, and energy equals mass times the latent heat of vaporization. Okay, so these formulas are really, really easy. So a question might go something like this. What mass of ice would require 10,500 joules in order to melt? Okay, so if I'm talking about something that is melting, which one of these two formulas am I going to use?
E equals MLF.
Right. MLF, freezing and melting. Okay, this is the one I want to use. All right, so I've got to find M. They told me E, 10,500 joules, and I know what LF is. It's 333 joules per gram. Okay, so all I have to do for this question is go, all right, LF, 333 joules per gram, okay, and E equals 10,500 joules. E equals MLF, okay, and I manipulate for M. So 10,500 joules divided by 333 and will give me mass. So all right, so 31.5 grams. That's about 30 mils, 30 milliliters of ice or so. Okay, 31.5 grams. Okay, does that seem like a lot of energy? It is, okay? And this isn't very much ice. That's why a whole bag of ice can keep a lot of stuff cold for quite a while. Okay? It has a large ability to absorb heat energy as it melts.
On a test or a quiz, would we have to do other substances other than water?
Only water. Yeah, because I don't have the numbers for the other substances. This isn't normally how we do this. This is one of the things we've shortened. Okay? Normally, what we would have you guys doing with this stuff is, I would say, how much energy is required to heat ice from minus 25 into steam at 105. Okay, which would require you to do an E equals MC delta T calculation for how much energy would be required to warm the ice. Then an E equals MLF calculation to calculate how much energy would be required to melt the ice. Then an E equals MC delta T question to calculate how much energy would be required to heat the water. An E equals MLV calculation to calculate how much energy would be required to evaporate the water. And then an E equals MC delta T question in order to calculate how much energy would be required to heat steam. Not mathematically difficult, but time consuming. Right? Hey. Okay. Okay. Everybody understand what we're doing there? Okay, so you have to use MLF if we're talking about melting or freezing. Okay, it's easy to remember, F for freezing. Okay, and we have to use MLV if we're talking about vaporization, V for vaporization or condensation. Pretty easy to remember. Okay, tomorrow we're going to go over biomes. Okay, I'm hoping to get that all done in tomorrow's class. Okay, it'll be tight, but I can probably finish it all in tomorrow's class, which would give us Friday to do a Unit 4 exam review. All right, and then the Unit 4 exam is on Monday. It has been shortened, okay, because obviously there's some stuff that's not going to be on there now that's normally on there. So it's shortened, but it's going to count, same as your other ones, so it's a really good opportunity to boost the unit exam portion of your mark, because quite frankly, it's a really easy test because there's so little on it, okay, and it's so short. Okay? 22 multiple choice and 7 written. Like, it's really, really short. No quizzes. I said that the first day, man. Got it. Okay, so no more quizzes. Yeah, no more assignments or anything like that. Okay, so if I can get you guys to clear up your desks so I can come around and spray them off.